stages yours.
Yeah, thank you so much for the very kind introduction. And of course, thank you very much for having me. But before I get into the weeds of the actual talk, I should probably preface this by saying that I am not a condensed matter physicist. And so for the most part, I think about gravitational waves, things, and black holes. So I'm going to try to use terminology that's perhaps more adjacent and closer to condensed matter physics, and make the distinction clear when I'm using which terminology. But if some piece of terminology is unclear, please do just jump in. I think that way it's a lot more productive. Okay, yeah. So I'll be talking about vortex dynamics in strong gravitational fields, and so perhaps from a condensed matter perspective, vortex dynamics is interesting, but why study this in the context of gravitational fields? So basically, there's two pieces of motivation one can bring up. So first is the question of dark matter. So basically, we know that some fraction of the matter that we believe to exist in the universe we can't see, and so we call it dark matter. And basically, that's all we know about this. In particular, we don't know what the fundamental nature of dark matter is. And of course, there's various ways to explain this. And one particular way is this fuzzy dark matter paradigm, basically a buzzword that you may have heard of. It's basically the idea that you can model dark matter, cold dark matter, by non-relativistic scalar fields that can clump into bound structures like halos of galaxies, and then also form self-gravitating kind of solitonic cores, which kind of sit at the center of each halo. And because all of this is described by basically a complex scalar field, you can also have vortices forming both in the halo and the solitonic core, and interactions of these solitons. Basically down here is a picture of the phase during the merger of two spinning solitons. And if this doesn't look familiar to you at all, then okay, don't worry, I'll explain this in basically the first part of this talk, where I'll be focusing on these self-gravitating solitons. But then a second piece of motivation is more particle physics heavy, and that is the strong CP problem, which is basically a problem in the strong interaction where the QCD is satisfying the CP symmetry, but basically there's no good fundamental reason why that should be the case. And so in some sense, it's a fine-tuning problem where a particular term in the Lagrangian is basically set to 0, but it's not really a good reason why it should be set to 0. And then back in the 70s, people came up with ways of solving this kind of dynamically by introducing a new scalar degree of freedom, which basically multiplies this term that violates the CP symmetry, and the scalar field is then kind of dynamically driven towards 0, such that this term in the Lagrangian is indeed 0 or very small. Now, this, of course, is somewhat related also back to the dark matter paradigm through the production of axions, which can also act as dark matter in certain parts of the primary space. But again, in this context, you're introducing a new scalar degree of freedom, which can lead to vortices, in this case, in the early universe. Okay, so basically, in the second part of the talk, I'll be focusing on vortex dynamics in the early universe, kind of motivated through questions related to the strong CP problem. So the bottom line is that I believe there's a sufficient amount of motivation to try and understand scalar field dynamics in gravitational fields, and specifically try and understand vortex dynamics in strong gravitational fields. Okay, so in the first part of the talk, I'll be focusing on this particular scalar model. So basically, Lagrangian L is the Einstein-Hilbert part of the Lagrangian. So basically, just the Ricci scalar R, and then capital G is just the Newton's constant. If you vary this with respect to the metric, then you'll just get the Einstein equations. So gravity. And then the second part is basically complex scalar fields. Basically a vanilla complex scalar field phi with some potential that only depends on the magnitude of phi. So basically, if you're familiar or if you look at Lagrangians often enough, then you can already see, okay, there's some global U1 symmetry that will be important in just a second. Okay, so in the solution space of this theory, you can find things that are called scalar solitons, or perhaps in my corner of the literature, they would be called boson stars. But yeah, for the purposes of this talk, I'll just use the two interchangeably, but hopefully only use the word soliton, which I hope is more familiar to the condensed matter community. But the bottom line is of what this is basically it's just a gravitational bound state of scalar matter. Okay, so like imagine you have some scalar field that kind of clumps up into some overdensity, and then gravity, its own gravity, kind of keeps it together and stops it from just dispersing away. Okay. So the field profile of these solitons is the following. So you basically have a harmonic time dependence, e to the I omega t, where omega is some frequency. And a harmonic azimuthal dependence, e to the I m phi, where m is some azimuthal index m, that's just an integer 0, 1, 2, and so on. Then the potential that I'll be looking at, I'll be considering throughout the first half of the talk is basically the following. So you can just consider the mass term, which is shown in orange here, which is basically just a phi squared term in the potential. But then I'll also be talking about repulsive self-interactions and what is typically called in my corner of the literature solitonic self-interactions. It's not too important why it's called solitonic, but it's basically just a phi to the 4 self-interactions such that there's a secondary minimum in the potential. But really, these self-interactions won't be too important for the kind of qualitative picture that I'll be drawing in a second. So yeah, it's not too important. I guess the important part is that all of these contain a mass term. So at 0 field value, the potential goes to 0. Okay, but because of this mass term, these bound states at large distances, the magnitude of these bound states, the magnitude of the scalar field, decays exponentially quickly. Okay, so you have this overdensity of scalar matter, and then it kind of, as you move away radially away from this overdensity, the magnitude of the scalar field will just drop exponentially to 0. Right, so I already mentioned that this Lagrangian has a global U1 symmetry. It's basically, if you send phi to phi times e to the I alpha, where alpha is some constant, this Lagrangian is invariant under this transformation. And so this implies the existence of a conserved quantity, which I'm just going to call charge throughout the talk. So this charge Q is basically just some number. And as it turns out, the angular momentum of these gravitational bound states, J, is quantized in this particular way. So basically, the angular momentum is equal to m, which is the azimuthal index, so some integer, times the charge Q. Okay, so you can have non-spinning stars, which are basically m equals 0, but then you can also have spinning ones, which are basically m not 0. But certainly you can't have any states which have angular momentum somewhere between 0 and Q, for instance. Okay, so there's a quantization of the angular momentum states. And as you may have already noticed, rotating solitons, so those ones that have m not equal to 0, are basically just vortex lines. So this you can very readily see by looking at this field profile. So if you set t to 0, then the azimuthal dependence is just e to the I m phi, and so the phase goes as you go around the center of the soliton, the phase will pick up a factor of 2 pi m. Which is basically the definition of like an M vortex, let's say. Okay, so to give you a bit more intuition for what these look like, so on the top right, I'm showing you surfaces of constant scalar field magnitude for a spherically symmetric soliton, meaning for an m equals 0 soliton. Okay, so it's just spheres, and then yeah, as I mentioned, the magnitude will just decay exponentially as you go away from the center. Don't worry too much about what stable light rings are. It's not important for this talk. And then the rotating counterparts, so like let's say m equals 1 or 2 or 3 or so on, the surfaces of constant scalar field magnitude take this toroidal shape, basically because you have a vortex line that pierces the center of the star. Okay, so the way to picture this is you have a vortex line at the center, and then you just attach some scalar matter to it through its self-gravity. Okay. Okay, great. So to kind of connect this perhaps a bit to terminology that you may be more used to, if you take the Newtonian limit, so of course this is just basically Einstein-Klein-Gordon theory. If you take the Newtonian limit, then this will just reduce, or the non-relativistic limit, this will just reduce to the Poisson Gross-Pitayevsky equations. Poisson basically because, well, that's the, the self-interactions are kind of the Newtonian potential. And so in that sense, these solutions that I'll be talking about are kind of the relativistic counterparts of these Newtonian solitons that you may be familiar with. But in fact, the fact that they're relativistic won't be all too important for most of what I'll be talking about, except for the very end, and I'll point out exactly when it's important. Okay, so what I'll be interested in describing in the next, let's say, 20 minutes or so, is what happens when these objects start merging, and in particular, what happens to vortex lines during these nonlinear merger processes. So in the community that I'm from, which is basically black holes, binary black holes, gravitational waves, the way things kind of merge together is basically in a binary context. Okay, so basically you imagine these are two black holes. And these are gravitationally bound. These are like, in a binary orbit. They orbit around each other. And so they emit gravitational waves. And these gravitational waves will carry away angular momentum, which basically just means that over time, the distance between the objects shrink, and they become more and more bound as time goes by, and they emit gravitational waves. Eventually, the separation becomes so small that they start merging, and that this is a highly nonlinear process, and then eventually will settle down to some final state that could be something. Now, if we were to replace let's say these black holes by two solitons, then this process will happen in a similar fashion, but there will be some key differences. So in the in-spiral, for the most part, this will still be driven by gravitational waves, meaning that you have this binary orbiting around each other. It will send out gravitational waves. Scalar interactions are small, and therefore the separation will shrink adiabatically as you emit gravitational waves. But I already mentioned that the magnitude of the scalar field would decay exponentially away from one of these solitons. But what this also means is that the overlap between let's say soliton 1 and soliton 2, like in the binary, will also go exponentially as e to the minus some number times the separation. Okay. Now, what this implies is that as these objects come closer together, the scalar interactions are basically exponentially enhanced. Okay, and to the point that at merger they will basically be very, very important for the merger product. But already in the in-spiral, you can see some things that are happening. Like a couple of years ago, or I guess almost 2 decades ago, people thought about this in a slightly different context. But basically, what they found was that if you have such a setup, and the object 1 has some frequency omega1, soliton 2 has some frequency omega2, and potentially has some phase offset alpha, then there's a scalar force that acts between these two objects that kind of goes like this. So it's a cosine of the difference in the frequency times the time plus some phase offset. So this is kind of peculiar because in some sense, the nature of the force oscillates in time. So it's like sometimes it's attractive, sometimes it's repulsive. And so basically what this means is that, you don't just have the gravitational attraction and the gravitational wave formation driving the in-spiral, but now you also have this additional force that influences the dynamics. And basically this additional force impacts or imprints itself on the gravitational wave emission, and it kind of looks like some kind of dephasing in the gravitational waves. So yeah, if you're interested in more of the details, then yeah, the details are given in this paper. But here really I want to focus on the merger part, because that's where all the scalar field dynamics will happen, and that's where it will be important to understand what vortices are doing during that phase. Okay, so the kind of 2 key questions I'd like to address in the next couple minutes are basically the following. So first, what is the role of vortices during the merger? And in particular, if we take 2 non-spinning solitons, can we form a spinning soliton out of it? And how does this happen? Under which conditions does this happen? And then secondly, if we started out with 2 spinning solitons, so imagine these 2 blobs are actually 2 spinning solitons, then each of them has a vortex line. And then what happens to these vortices at merger? Do they form another rotating soliton? Do they do something else? What happens? Okay, so let's first understand the first question. So basically, can we form a rotating soliton from two non-spinning solitons? And before I go there, let me provide you a little bit more intuition of what I'm actually talking about. So here I'm showing the scalar field magnitude of a particular, solitonic binary that is gravitationally bound. So basically, they will just orbit around each other. And as I play this movie, okay, as I described, you have this binary that orbits around each other. And then it emits gravitational waves, so the separation will decrease over time, and then eventually they will touch and merge into some, highly perturbed but still, kind of quasi-stationary state that will just, sit there, and all these modes will decay over time. But what you've already noticed is that okay, something is slightly confusing here because you started out with two non-spinning solitons that were in some orbit. So there was some orbital angular momentum in the system. But somehow the remnant was also a non-spinning soliton. So somehow the remnant didn't want to form a spinning soliton, which would require a vortex to appear somewhere. And instead, it kind of decided, okay, I want to get rid of all my angular momentum and settle down to a non-spinning state. So this is already kind of confusing, and it hints at the fact that you have a quantization of angular momentum states. So if you're not having enough angular momentum to jump to the first state, then you will not jump to the first state. Okay, but perhaps a bit more concretely to analyze when this in fact happens, I should point out the following. So yeah, to the best of our knowledge, the people hadn't quite understood exactly how this worked. If you started out with two non-spinning solitons, you tried to merge them, how you could generate one that was spinning. But yeah, so we looked at this and we were curious, okay, what actually happens? Why is this the case? And so basically we came up with various different conditions. So yeah, I'm writing down three kind of schematic conditions. So the first one is somewhat obvious in the sense that, okay, you have at fixed charge, and by charge, I mean, this U1 charge, that's basically just counts the number of bosons in these states. At fixed charge, you want the following to be true. You want that the energy contained in the binary is larger than the energy of the final spinning soliton remnant. Okay, so if it was the reverse, obviously you would need energy to generate such a vortex. But if it's the former, then it's energetically favorable to actually form the spinning soliton. So this is somewhat of a no-brainer, but okay, it's a necessary condition. Secondly, and this is what I already alluded to, is that, okay, you need to have a sufficient amount of angular momentum because of the quantization. So if you only have, some fraction of the necessary angular momentum, you will not form a spinning soliton. But conversely, it also means that if you have too much angular momentum, this might also be a problem. I won't touch on this too much, but yeah, if you're interested, you can ask me a question after the talk. But perhaps crucially, and this is what people had missed, is that at the point of contact, you need to have a sufficiently large phase gradient from one soliton to the other soliton. So basically what I mean by this is that the complex phase that is associated with one and the other soliton has to have a sufficient difference, sufficiently large difference, such that vortices can form where the gradient of the phase is very large. Okay, so let me make this a bit more concrete. So let's consider the binary profile. So again, I'm taking two individual solitons. Soliton 1 has some frequency omega, and then soliton 2 has the exact same frequency omega, but plus some constant phase alpha, which I can specify. Okay. So the situation I'll be considering is basically shown in the schematic here on the right. I have two solitons, and there is some impact parameter here. Basically, if the impact parameter was 0, then the angular momentum in the system were 0, and then of course you cannot form a spinning soliton. So the basically impact parameter just controls the angular momentum in the system. And then the alpha, so this constant phase offset, is just set to pi. So basically here the idea is that at the point of contact, what will happen is that the phase gradient will roughly be pi between these two objects. I think there's a.
It looks like Wei would like to ask a question. Yes.
Yeah, sorry to interrupt, Nils. I have a quick question here. I'm not quite sure about the sufficient angular momentum argument. I imagine, say, if you have a soliton with a vortex in it, and if you put the vortex at the center, definitely you have a large angular momentum. But if you shift the vortex towards the surface, the angular momentum can diminish it can actually go down to zero if you get close enough to the surface. So the angular momentum for the soliton carrying one single vortex can be tuned indeed. It's not like a step function.
Right.
Can you comment on that?
Yeah, so okay, right. So what I mean here is basically the angular momentum of a stationary state. So these spinning solitons, so basically these solutions associated here, they're stationary in the sense that, you know, the magnitude of a scalar field doesn't depend on time. And so in that sense, that's what I mean by the angular momentum quantization. So I want the final state to be some stationary state. And so I imagine what would happen if I, you know, displace this vortex from the center is that you know, the only stationary states available to the system are either one where it is at the center or the other one where it's not in the soliton at all. So it's kind of ejected out.
Well, but you can have a vortex, say a single vortex, say near the surface, but then it propagate in a circle, essentially propagating together with its image vortex, right? Mm-hmm. So this is not a stationary, I mean, static solution, but it's definitely a stable solution. The vortex simply rotate around the center axis.
Right. Yeah. So yeah, I see what you're saying. I guess what I'm trying to say is that but that we were aiming for these stationary solutions. In fact, now thinking back, I don't think we actually ever, well, yeah, so this behavior does occur sometimes, that, you know, you have this vortex kind of circling about some center, but we never found this to be a particularly stable situation. Yeah.
Okay, thank you. Sorry to interrupt you.
No, this is great. Let the questions keep them coming. Okay, great. So the setup is this, and so yeah, the key idea here is that, you know, have a large phase gradient across at the point of contact of these two objects. Okay, so to you know, basically demonstrate that indeed you know, the spinning solitons do form. By spinning here, I mean the stationary solution. Basically we set this up and did some numerical simulation of, you know, the Einstein-Klein-Gordon system with this particular setup. And what I'm showing in the bottom left here is basically the magnitude of the scalar field as a function of time, and then, you know, just in space, basically reproducing this figure. And so what you can see is, okay, you know, they kind of come in and then they start merging, and well, it's kind of obvious. Okay, you have a vortex at the center of mass of the system, and you know, the scalar matter kind of gets attached to this vortex line, and over time it will kind of like settle down to a stationary but spinning vortex. And to kind of illustrate this perhaps a bit more, the role of the phase on the right, I'm showing basically the exact same situation, but now I'm multiplying the magnitude of the scalar field by the complex phase psi. So initially you just have this harmonic oscillation of the phase inside each soliton, and then as it starts merging, it will start rotating around the central vortex line. So let me play this movie. So here is just this harmonic oscillation of the phase in each of the solitons. And then they come in, and then it starts merging, and then you can see, okay, now it starts oscillating around the central vortex core. Okay, so this is just to demonstrate explicitly. Okay, you know, if you satisfy these conditions, then you will indeed be able to form this stationary spinning soliton. Okay, so now we know how to form rotating solitons. So what happens if we now put two spinning solitons in a binary? So instead of, you know, considering two non-spinning solitons, now we have two spinning solitons. And the setup is, you know, exactly the same. We have some binary that is kind of gravitationally bound. And another question is, okay, what happens during the merger? What happens to these vortex lines? And so as they come back in, you know, some nonlinear merger process occurs, and suddenly you're left with two non-spinning solitons that kind of flung out, and then they come back in and kind of start bouncing off each other. Okay, so me, from kind of the astrophysics point of view, I was extremely confused as to what was happening when I first saw this. Maybe you are more familiar with these things, but yeah, so I had to break it down to actually understand what was going on. So let's kind of do a kind of snapshot by snapshot. So what I should say before explaining this is that these are two identical solitons, meaning that they have the same energy, the same frequency, etc. In particular, the setup is such a way that the spin angular momenta of each of the solitons point in the same direction, but they're anti-aligned with the orbital angular momentum. Okay, so in the top left, these white arrows indicate the sense in which they orbit, so they kind of orbit counterclockwise. And so the orbital angular momentum is anti-aligned with the spin angular momentum of each of the spinning solitons. Okay. And then at the bottom here, you can see the phase corresponding to the snapshot. And okay, what you can see is that these blue circles indicate, let's say, +1 vortices associated with the solitons. But then you can also see this red circle indicates a -1 vortex associated or sitting at the center of mass of the system. Okay. And so in the second column, you can then see, okay, during the merger, what's going to happen. Okay, at the bottom, you can see, okay, we have a +1, we have a -1, and another +1 vortex. And what you can already guess is going to happen is that, okay, the +1 and the -1 will just merge and annihilate. And then you're just left with one +1 vortex that will just replace the one at the center of mass. And so in the third column, you can see exactly this happening. So at the bottom, you can see, okay, we're left with just one vortex. And in the top, you can see, okay, now we kind of split up into these two blobs that are separated by this vortex. But more importantly, they're separated not just in space, but also in terms of phase. So like the color here is, let's say, some reddish and some bluish on the other side. So if you consult the color scheme, it kind of makes sense that there's roughly a phase offset of pi between these two blobs. Okay. So in the fourth column, it's just a bit more pronounced. Basically, you have this vortex at the center separating the two non-spinning solitons. And the first solitons have a phase offset exactly pi. Okay, so that kind of explains why they start bouncing off each other, is because there's this vortex line at the center that doesn't let them merge. And so the final state is basically just that. You end up with this, bouncing situation where you have these two solitons that don't want to merge. But perhaps more interesting is that now these white arrows also indicate the sense of orientation, the sense of orbit. Okay, so here now the binary orbits clockwise, even though initially it orbited counterclockwise. And so the reason for this is the following. So the spin angular momenta of the two solitons are actually much bigger than the orbital angular momentum initially. Okay. And so the total angular momentum has the opposite sign than the orbital angular momentum. Okay. So during this nonlinear merger process, all the angular momentum, especially the spin angular momentum, is converted into orbital angular momentum. And so that's why the orbital angular momentum changes sign as this merger proceeds, and because the final solitons are non-spinning, so they don't contain any spin angular momentum. Okay, so this kind of explains what I found when I first saw it, strange behavior during the merger of these spinning solitons. Okay, so I did promise that I was going to show some gravitational waves. So here are some gravitational waves. So basically here I'm considering a similar kind of binary. So we have two spinning solitons. They are not identical solitons, meaning that the size is slightly different. But anyway, these are just kind of technical details. So if I play this movie, then okay, you will see them orbiting, which in this gravitational waveform corresponds to kind of the early times where the amplitude of the gravitational waves kind of just oscillates sinusoidally. Okay, that just corresponds to the orbit of this binary around each other. But then looking at this movie, you can see that there will be some enhanced interaction, there was some repulsion, and then during the merger, they again broke up into two non-spinning solitons that then kind of got flung out at large velocities. And so in the gravitational waveform on the left, what you can see is that, at this point, what happened is first that the amplitude of the gravitational wave decreased temporarily. This you can see here. This is basically because there was some repulsive push that's temporarily increased the binary separation, which then leads to, you know, a reduction in the amplitude of the gravitational waves. And then secondly, during this you know, nonlinear merger process, there was some large blip, okay, but then of course you're not left with like kind of a single remnant that just kind of rings down and slowly settles to some stationary state, but instead you're left with, you know, two things that are kind of flung out at large velocities. So basically what this means is that the gravitational wave emission of this will be very, very small, and this is exactly what we see here. It's basically just, you know, some blips, but then that's basically it. It just goes back to zero. Okay. So you know, if we compared this to say, you know, a binary neutron star, like astrophysical objects, binary neutron stars or binary black holes, then the inspire will look very similar because, well, you just have two massive objects that kind of orbit around each other. But then the merger will be fundamentally different because, you know, both for neutron stars and black holes, the final remnant will be just a single remnant, as opposed to two bits that are kind of flung out at large velocities. So I guess the, you know, one goal of generating these waveforms is to see, okay, can we actually, with gravitational wave detectors, tell if, you know, these very compact scalar solitons actually do exist, and, you know, were produced perhaps through some dark matter condensation. Okay, so this brings me to the end of the first half of the talk. So maybe this is a good time to pause and ask if there are any burning questions. If not, then yeah, let me move on to the second part. So here, I will be talking again about vortex dynamics, but now in the context of early universe physics and early universe cosmology. So it's a slightly different setting. In particular, the scalar field model that I'll be looking at is also slightly different. So here I got rid of the Einstein-Hilbert term, so let's just forget about gravity for the moment. And then, okay, it's just a complex scalar field again, capital phi. And then we have this particular potential here. So this is just the, you know, wine bottle potential that I'm showing on the right. So basically at the, you know, at the center, so, you know, at zero field excitation, if you want, the potential takes on some finite value. Then it goes down towards the vacuum state, and then, you know, it goes back up. And so if you split the scalar field in this following form, so you have some, you know, magnitude rho and some complex phase theta, then, you know, rho will kind of explore the potential kind of radially outwards in this diagram, whereas theta will kind of just go around the central line in kind of a circle. Okay. So what this implies is that, you know, the radial mode rho has some mass mu, which is determined by mu in the potential because basically it can explore the potential. Okay. In contrast, the angular mode theta, well, it just goes in circles, and so it doesn't actually see the potential. It just sees, you know, one particular value, and so it's basically a massless mode. Okay. Now, crucially, there's the vacuum state is you know, in contrast to what I talked about before. The vacuum state is now no longer at the center, but instead it's kind of down here in the minimum in this circle. Okay, so basically where rho squared is equal to v squared, and, you know, it's this particular combination, but it's basically the quote unquote vacuum expectation value of this radial mode, and in particular it's some circle down here. Okay. But again, because, you know, this is this just depends on the radial, so the magnitude of the scalar field, there's a conserved U1 charge associated with this Lagrangian, which again will be important in just a second. Okay, so what are vortices in this particular model? Well, basically they're kind of very similar to what I was already describing. So perhaps in the cosmological context, one would call them more cosmic strings than vortices, but I'll be using the two terms, although there is a slight technical difference, I'll be using them interchangeably. Okay, so basically asymptotically, you know, at spatial infinity, so very far away from the vortex core, the radial mode will just, you know, go towards the VEV, so V, so it will just sit down in this, you know, in the minimum of the potential, minimizing the potential energy. But as you approach the vortex core, you know, as R goes to 0, by R, I mean just the distance from the vortex core, then the radial mode must go to 0. And so basically the radial mode kind of climbs up this potential well towards the peak. And then, yeah, okay, the angular mode kind of wraps around in a circle. So basically, you know, as you go around the vortex core in real space, theta will pick up, you know, a factor of, let's say, 2 pi. Okay. So in the context of cosmology, and perhaps this is also relevant in condensed matter physics, you know, there's various production mechanisms, but one particular one that's relevant in cosmology is the Kibble mechanism. So basically, it's a way of, you know, thermally producing vortices through some phase transition where you kind of change this potential adiabatically as a function of temperature. It's not too important, but basically what we were interested in and what we wrote in the paper that came out last week is on the archive now. What we were interested in, okay, is there a different way of producing cosmic strings or vortices in the early universe in this particular scalar model, okay? And so in the context of you know, early universe cosmology, what you're interested in is basically a scalar field profile that's, you know, spatially mostly homogeneous, so just spatially constant with very small fluctuations, okay? And so if we just ignore these small fluctuations and only care about the spatially homogeneous part, then you know, the dynamics simplify significantly. So you know, the equations of motion of these are basically, you know, a set of, you know, second order PDEs, which are in principle quite difficult to solve. But if you only care about kind of the spatially homogeneous part, then things simplify as I said. So how does it simplify? Okay, let's focus on the spatially homogeneous excitations, meaning those modes that don't have whose wave number is 0, basically. So just, you know, spatially constant, all spatial gradients are 0. Basically, this solution is just characterized by a bunch of numbers. So basically, you know, the radial excitation rho 0 is just a function of time, not a function of space. And similar to with the angular mode. Now here, in this particular context, we'll be interested in mostly in a situation where the radial mode is displaced from the vacuum expectation value. As I understand, this is slightly different from typical condensed matter systems where the radial mode wouldn't be displaced from the vacuum expectation value. But yeah, so we are interested in this particular context. Of course, there's a conserved charge. And so what this implies is that you can remove one of the degrees of freedom of the system. So basically the time derivative of the angular mode, so theta dot, is equal to some constant J naught divided by rho naught squared. Okay, so J naught is basically just some constant. The nature of what this is not too important, but it's just some particular number which helps us eliminate one of the degrees of freedom. So basically what we did here is we mapped, you know, basically this PDE or, you know, the dynamics encoded in the PDE in the dynamics of just a simple classical particle that is trapped in a particular effective potential, which results from, you know, imposing charge conservation. So the potential that this actually turns out to be is shown in the bottom left. So here, of course, this potential depends on this J naught value. So here I'm just plotting it for various J naught, but really the key features are independent of J naught. Basically, the features are that, you know, at rho naught going to 0, there's an angular momentum barrier. So basically, rho naught cannot go to 0. And at large distance or at large rho values, the potential grows, which basically just means that, you know, a classical particle cannot explore those parts of the potential. And so if we focus on, let's say, the blue line, meaning, you know, J naught equals to this particular value, and I place a particle here and let it go, what will happen is it will roll down this potential and kind of come back up. There's a classical turning point here. It will come back down, and it starts oscillating about this minimum, okay? And so what this looks like in field space is the following. So here on the right, I'm showing you basically the real part of the scalar field versus the imaginary part of the scalar field. So it's basically just a top-down view of this wine bottle potential. And in red, I'm indicating the minimum of this effective potential. So for, you know, for a very small J naught, the minimum here of the effective potential coincides exactly with rho naught equals to V, okay? So the red circle just indicates the minimum of the potential. And so if I go through this exercise and, you know, I place a particle somewhere here on the blue line and let it go, it will oscillate around this radially, and that's exactly what you see here. In this particular schematic, we also gave it like a slight kick in the angular direction. So basically what happens with this particle is that it moves angularly around the circle like this, and then oscillates in the radial direction about this minimum, okay? So basically what I'm trying to say here is that we have some spatially homogeneous field configuration that's like slowly oscillates around various minima in field space. Okay, it kind of behaves like this. Now, of course, you would say, okay, now we have a spatially homogeneous field configuration. Clearly, there's no vortex here because that would be spatially very inhomogeneous. So how are you thinking of generating vortices in such a context? And as it turns out, this kind of like almost harmonic oscillation of the field is actually parametrically unstable. Okay, so what does parametric resonance mean? Basically, there's an instability that drives spatially inhomogeneous modes. So basically, the oscillating zero mode, by zero mode I just mean the spatially constant mode, is unstable to modes that have wave number that are basically non-zero. Okay, so they're order one fraction of the mass scale. It's not too important, but basically what is important is that they're non-zero. Okay, so you will grow spatial inhomogeneities, and in fact you grow these exponentially quickly. Okay, so you grow these spatial inhomogeneities exponentially quickly with some rate capital gamma, which again is some order num wonder of the mass fraction of the mass scale. Okay, so to give you a bit more intuition for what this parametric resonance looks like, here I'm showing basically plotting the growth rate gamma tilde. Gamma tilde is just gamma divided by mu. As a function of the wave number, k tilde, again, k tilde is just k divided by mu. And okay, for various different parameters, you get different shapes, but we can focus just qualitatively on the purple line. And what you can see is that, across a large range of wave numbers, these modes will grow exponentially with, a rate gamma tilde. Okay, so what this means is that we start out with a spatially homogeneous field configuration, but exponentially quickly we're pumping energy into spatially dependent modes. Okay, and so these spatially dependent modes look something like this. So on the left, I'm showing basically the angular mode theta minus the average of the angular mode theta. Okay, so the average will contain just the zero mode, the spatially constant mode. And so basically here I'm just subtracting out the spatially constant part. And you're left with just these spatially inhomogeneous, configurations where sometimes it's displaced in a plus direction, sometimes in minus direction away from the zero mode. And similarly, you can also see that in theta dot, so it's basically just a time derivative of the angular mode. You can see that some patches have a positive field rotation. By field rotation, I just mean theta dot, and some have like a negative theta dot. Okay, so here now you say, okay, great. Now we have a spatially constant field configuration that is unstable to some modes that grow exponentially quickly. The natural question is, okay, what happens when these spatial modes grow into the nonlinear regime of the theory? Okay, then something dramatic must be happening. And that's exactly what we found. So we basically did some simulations of these systems. And what we find in the end state is basically shown in these series of plots. So focusing first on the left, you can see the phase as a function of two spatial dimensions, x and y. And so what you can see is that, okay, there's a bunch of vortices everywhere. So if you're not used to looking at these plots very long, then my cursor indicates like one vortex here. And as you go around the tip of the cursor, you can see that the phase will pick up a factor of 2 pi, basically. And so there's one here, there's one there, and then there's a bunch of vortices in this domain. Okay. And then in the central plot, I'm showing theta dot. So basically, okay, just like before, we had these regions where theta dot was positive, and there's regions where theta dot is negative. And so basically just, slightly different colors. And if you squint, you can see that the vortices shown on the left here actually exactly align with the lines where the color changes. Okay. So these we call domain boundaries. So basically just the boundaries that separate these regions where the angular mode goes one way versus the other way around the circle in the potential. Okay. And then on the right here, I'm showing the basically the radial mode. And you can see that the radial mode obviously goes to 0 wherever there is a vortex. But more importantly, it kind of forms these filaments, which, rho over the VEV is small in exactly those regions where where theta dot changes sign. So basically where the color changes. Okay, so at these domain boundaries, theta dot is very small or 0, and rho over the radial mode is also very small. Okay, so the vortices kind of align with these domain boundaries. Okay, so what are the conditions for vortex formation in such a system? Basically, okay, we're providing a lot more details in the paper, but here let me just say that one necessary condition that we found was that there has to be a sufficiently large space-time gradient of the angular mode. So by space-time gradient, that just means this expression here. So basically, partial mu of theta, the angular mode, squared. Which is basically just, the spatial gradient squared of theta minus the temporal gradient squared. Okay, so I already noted that the vortices align exactly with where theta dot is 0, which of course minimizes this the subtractive component. And okay, I haven't said it, but basically on these domain boundaries, the spatial gradient of the phase is also very large. And so basically the space-time gradient is very large, which makes them satisfy the condition that this gradient has to be large to form vortices. Okay. And then secondly, there's of course an energetics argument to be made. That is, if you don't have enough energy to form these vortices, then of course you're not going to form them, which is basically a condition on the excitation of the radial mode away from the VEV, which we lay out in more detail. And in the interest of time, let me skip over this. Okay, so now we saw, okay, we have these exponentially growing unstable modes. They reach the linear regime eventually, and then they form these vortices. So what happens over time? What happens to these vortices? How do they evolve in time? And what's the end state of the system? So before getting there, I need to note that we found a somewhat peculiar behavior. And we call this vortex confinement, but it's basically, we found that both in 2 dimensions as well as in 3 dimensions, so 3 dimensions shown here, the vortices or the strings were basically confined to live on these domain boundaries. Okay, so here in 3D, I'm indicating the domain boundaries by basically just small radial mode values. So basically, these blue surfaces are isocontour surfaces associated with some particular value of the radial mode, which is, supposedly small compared to the vacuum expectation value. Okay, and then in these white dots indicate where the strings lie, and so both on the right as well as on the left, you can see that the strings are kind of completely confined to these 2-dimensional filament surfaces, which are basically these domain boundaries separating regions where theta is positive versus negative. Okay. And what we found is that dynamically, okay, these are confined to only move on these domain boundaries, only on these surfaces, and they never kind of escape out of the surface. Okay. Okay. So what this implies is that, okay, what could happen is that you will generate a vortex, or you will generate a string loop, and this is then confined to live, only on these domain boundaries, and eventually you will find an anti-vortex to annihilate with. Okay. And so then, okay, then you generated a vortex, but somehow it disappeared. And so then subsequently, you might be able to generate another vortex, and that can, find another anti-vortex and then annihilate. Okay. And so what we actually found is that this process happens periodically. So periodically, you will generate a bunch of vortices. They will travel around these domain boundaries. They eventually find, a partner to annihilate with, and then they're gone. And then sometime later, this process repeats. Okay. So let me illustrate or kind of give you an intuition for why this periodicity appears. So again, just noting that, okay, for the vortex formation condition was that we needed to have a large space-time gradient, which is basically large this expression. Okay. So what this means is that vortices are most prone to form on domain boundaries where theta dot is 0, which of course maximizes this expression. And so these domain boundaries separate regions of counter-rotation. So what this means is basically just the boundaries are where the color changes, meaning where theta dot changes sign, and therefore must be 0. Okay, but then we also learned, okay, there's this vortex confinement in such a way that once you generated a vortex, it will propagate only along this domain boundary. Okay, but of course, since producing a bunch of vortex pairs everywhere, eventually, one of the constituents of the pair will travel along the domain boundary. They'll find an anti-vortex and it will annihilate. Okay. And so to understand the periodicity in this, one has to understand the fact that we need to also have large spatial gradient of the angular mode, okay? And so basically what we found is that if the spatial gradient, or basically the phase on one side with this phase on the other side of the domain boundary is roughly 2 pi, then you will pop a pair of strings or pop a pair of vortices, and then they start traveling around. But this difference in the phases on opposite sides of the domain boundary is built up dynamically. So if you look at the plot on the right again, if I pick a region where theta dot is let's say, I don't know, yellow brownish, and then a region where it is turquoise, basically what happens is that, okay, let's say the value of theta is exactly the same on both sides, but then they start oscillating the opposite way around the circle, right? So basically you will dynamically generate a large gradient. Once this large gradient, reaches, roughly speaking, 2 pi, then you will pop a pair of vortices, the gradient decreases, and basically you're not satisfying the condition anymore, okay? Then this pair, okay, this will annihilate and so on, but then you'll dynamically build up another gradient because this theta dot is non-zero, so you build up another gradient. Eventually it will be large enough to generate another pair of vortices, and so on and so forth, okay? So basically the timescales over which this periodicity, or the timescale of the periodicity, is basically set by 1 over theta dot. So basically over 1 over theta dot, you build up enough spatial gradient to generate a bunch of vortices, which will then, find anti-vortex pairs, they will annihilate, and then the process happens. Okay, just to kind of briefly put this all back together into one coherent picture, let me show you a movie of how this all works out in one go. So basically, we start out with spatially homogeneous field configuration. So here on the left, I'm showing the magnitude of the scalar field. In the center, I'm showing the time derivative of the angular mode theta. And on the right, I'm showing you just the angular mode. And so initially, okay, it's just, one color because it's just spatially constant. Then eventually, you will see spatially inhomogeneous modes grow exponentially. And then you'll see, in particular, on the right-hand side, you'll see that these strings start forming, or these vortices in this case, start forming periodically. They form, annihilate, form, annihilate, and so on and so forth. So let me just play this movie. So initially, the spatially homogeneous field configuration just happily oscillates in the potential. But eventually, you'll see at the center how these inhomogeneities grow and how they start growing exponentially. And eventually, they hit the nonlinear regime, where on the right-hand side, you can now see, I mean, it's hard to see because everything moves very quickly, but you can see that there's vortices forming and annihilating. So that's basically snapshots or time steps in which there's no vortices, and then at other times where there's a bunch of vortices. Okay, so in the interest of time, let me actually skip the cosmological context. So we also did all of this on an expanding universe background. There's certainly a lot of interesting dynamics there too, but perhaps the bottom line, the main takeaway there is that eventually these counter-rotating regions that I showed you here, as well as all the vortices, disappear because basically the densities dilute so far in such a way that you end up with no vortices, and the state just transitions to basically a scalar radiation state with some leftover coherent motion. Okay, so let me briefly summarize. So in the first part of the talk, I basically showed that spinning solitons can form, or stationary spinning solitons can form from basically non-spinning solitons and mergers or collisions of those. And secondly, that vortices play a central role during the collisions also of spinning solitons, and understanding exactly what these vortices are doing helps us understand how these spinning solitons merge. And then in the second half, I focused a bit more on the cosmological aspects of and where vortices appear in the cosmological context. And so there we saw that coherently oscillating scalar fields that are spatially homogeneous are unstable to basically parametric resonance, which drive modes that have some spatial dependence. And once these modes hit the nonlinear regime of the theory, then they will start producing vortices or strings, which then kind of happen periodically in time. And this all happens on these domain boundaries. Okay, yeah, let me leave it at that, and thank you very much.
Thank you very much for a really interesting presentation. We've reached 5 p.m. here in the UK, so before we go to questions, I will say that the next webinar is likely to be on the second Tuesday of April. We'll return to that by email a bit closer to the time. Do we have any questions from the audience? Well, maybe while we wait for questions, I have many. Maybe about the regarding the first part of your presentation. Are you aware of any lab systems with this sort of merger dynamics that might be relevant to, or at least somehow comparable to what you've been simulating?
Yeah, great question. I don't think it's a question I can answer. I think what I can say is that well, the solitons that I was considering are gravitationally bound, so I would imagine that would be hard to reproduce in a lab. What would be perhaps easier to reproduce in the lab is like most of the merger, like for most of the merger dynamics that I was describing, gravity isn't actually all that important, because all that gravity does is like, okay, it kind of solicits the merger, but it doesn't really take part in the merger much. So I can imagine that perhaps in a lab setting, there's vortex dynamics that I was describing that could be realized. Of course, subtracting the gravitational part there. How exactly that would be realized, I don't think I am the most qualified to answer that. No.
Well, I do know. I mean, I've myself worked on cue balls in an analog or quasi-particle system without vortices, though, in these things. But that is, to the extent I understand, not very far from what you've been describing.
Yeah, that's true actually. Yeah, a good point. Just briefly about this. Yeah, so right, so for cue balls, and I guess also spinning cue balls, this would, I imagine, I haven't done the calculation, but my conjecture is that, or my wild guess that I'm making right now is that the dynamics will be very similar to what I described. Yeah.
What happens if you have many vortices, not just one in each of the merging objects?
Right. So this kind of connects back to the question that came up during the talk. So so we focused on these stationary solutions, which basically just have a single vortex line threading them. I'm actually not aware of any solution that has multiple vortices. Like, so you're thinking of separated, like, let's say separated, m equals 1 vortices that are all kind of piercing the same object.
Well, I mean, if I'm thinking about a condensed matter system that rotates, often they rotate so rapidly that corresponds to an actual, like, an array of vortices rather than a single vortex.
Right.
And so then that would perhaps give, I don't know, different dynamics if that were the case.
Yeah. So the short answer is I'm unaware of such solutions in the gravity context. So one thing I can say is that so there are other contexts which I didn't describe here, but basically there what can happen is that you merge two non-spinning solitons, and you'll generate a bunch of vortices in that merger, and these vortices will then kind of start oscillating around the center, similar to what was described, or there was this question during the talk. But of course, this is a non-stationary state, so eventually these vortices will either disappear or things will collapse to a black hole. This kind of depends on the setting. But so in that context, I can imagine that you have several different vortices piercing the object. I'm not sure about stationary solutions in that context, but yeah, interesting question for sure.
Well, I encourage the audience to ask things. I mean, I'm kind of monopolizing the conversation now, but I did want to this is also kind of partially a comment, but in the second part, what you were showing reminded me of some time-dependent Ginzburg-Landau simulations that my collaborators in Helsinki are doing. This is to try to describe for example, continuous phase transitions into the superfluid state and what follows from the Kibble-Zurek vortex production there and so on. And well, while that's not exactly the same theory, that particular thing is actually related to experiments that we are running here in Lancaster. So that's kind of a detour into some sort of experimental lab analog systems.
Right. Actually, can I ask a worse question? I guess I'm supposed to be asked.
Sure.
So in that context, so I briefly mentioned that you know what we have been looking at is basically where the radial mode is displaced from the vacuum expectation value. But in these systems, is that also the case, or is it mostly that the radial mode sits at the VEV?
Well, so the superfluid transition itself is always second order, but there are two stable phases, A phase and B phase of superfluid helium 3, and the experiments are about understanding how you traverse the first order phase transition between these two phases if you've ended up in a supercooled A phase, for example. And one branch, or maybe even the dominant mechanism, is local heating into the normal state and then coming back through the second order transition, which then produces a mosaic of both phases, and occasionally you'll get the vacuum or low energy state winning this resulting competition. That's roughly speaking what's going on there.
Mm-hmm. Mm-hmm. Okay.
I'd be very happy to discuss that further by email or in private, but unless there are any questions from the audience, I think we are approaching the end of this session here. I also need to go myself, so let me thank the speaker for a very interesting presentation, and also the audience for being here today. And I will see you all in probably 4 weeks' time.
Bye.